I'll be talking about new innovation frontier with large language models for SOC security. My name is Mark Taranepur. I'm the chairman of the faculty and chairman of the ECE Electrical and Computer Engineering Department at the University of Florida. And I happen to be the co-founder of a company, a startup company in Florida called Caspia Technologies. So the complexity of today's designs made verification very, very important. And if you look at the numbers that are reported, the verification market cap has grown to more than $2.2 billion as of last year and continues to grow at a rapid pace. The focus when it comes to logical verification is actually on functional correctness, power, performance, and area optimization. But what's really right now missing in that verification aspect is the notion of security. The complex designs that we have today, then the interaction that we have between different IPs in the design has made security and its verification extremely difficult and challenging. There are all sorts of vulnerabilities, and more obviously comes in every day, has made security such an important problem for us to address. By the way, that timer doesn't work, so I have unlimited 45 minutes to talk. Yes, so with that, when it comes to security, a lot of times we associate incidents with the importance of that security problem. And this is usually done within software domain, network domain, when you hear major problems that happen. When it comes to hardware security, also over the past many years, there have been a number of important incidents that have happened. And the most important one that really brought security to the surface and to many companies' attention is actually meltdown and spec-ray vulnerabilities that happen on Intel chips. And this was mainly because of the attackers taking advantage of the out-of-order execution. And this was basically somewhat of a known problem. But until it was discovered and became available for everybody to test it out and use that vulnerability to provide proof of exploitation, it didn't get a lot of attention until that happened. When it happened, it actually brought Intel stock down for about 7 to 8% on that day, and that was the Intel stock, which we know it was about $150 to $200 billion, not today's $80 billion. The second one, which also made quite a bit of noise, is the attack that is called Alibaba's T-head, known as Ghostwrite. And what happened was this was a faulty RTL instruction that led attackers to do read-write operation into the physical memory itself. And this fault in the RTL code could have been detected and prevented, say, by the technologies that I'm going to be showing you today. But it wasn't obviously, and this became a major attack for data centers for Alibaba. So the list of these sort of vulnerabilities, unfortunately, has been increasing year after year after year. If you go back, and I see some familiar faces in the room, when they've been around hardware security for many, many years, they can attest to the fact that there was a time that every year we would have gotten, or every 6 months, we would have gotten one vulnerability. But today, almost every other day, we actually hear about vulnerabilities or variations of existing vulnerabilities: fault injection, privilege escalation, trace buffer, EM side channel, denial of service, row hammer, power side channel, access control, meltdown and spec-ray, and it's basically hundreds of variations of the vulnerabilities that have been introduced. Information leakage, trusted execution environment attacks, and so on and so forth. And majority of the time, this is not because our algorithms or architectures are weak, it's because the implementation is weak. We, in fact, often have very strong algorithms, but what happens during implementation and silicon implementation, because of lack of understanding that exists, it causes security issues. So to give you an example of the growth that we've seen in terms of introducing this and understanding this sort of vulnerabilities, similar to what we do in software domain, we measure that by the number of CWEs, or common weakness enumeration. A committee started in 2020, and as of now, more than 100 known CWEs have been reported, and description is on the web, in their website, and so on and so forth. That really tells you how fast the number of hardware vulnerabilities are growing. So verification is a must. And we have to do it at the earliest stages of the design process if we want to reduce the cost of verification. As I said earlier, the functional verification already takes up 70% of the total verification. I can't afford to have security to add another big percentage to the total cost. And we need to do this as early as possible. If you're familiar with the rule of 10, especially for those who are in testing and reliability, they know this rule very well, and that is, if you detect a defect at the earlier stages, you're going to be basically saving 10 times more if you do that. And the same holds true when it comes to security. The objective here is this notion of shift left, because it gives you a lot more flexibility, not only to detect the vulnerability, but also to be able to address the vulnerability. And when it comes to security verification, the notion of verification is not as different as what we know with regard to functional verification. In functional verification, we usually start with linting process, where it performs a code audit. Then we go into formal approaches and create assertions. And then we go into more dynamic environment where we do sometimes hardware, software simulation, or have emulation platforms like Synopsys ZeBu or Cadence Platinum, and so on and so forth. And we're able to run the entire design on a real traffic and try to target more of the functional bugs that exist. Same is done with security. We will perform functional security linting, then we will perform formal security verification, and then dynamic security verification. The key really to bring the cost down, and some of you know this very well, the cost of security, the cost of testing, and the cost of design for manufacturability or design for anything should not bite into the semiconductor revenue per transistor. This is a non-negotiable. So to do this, then we need to find a way to be able to minimize the cost of security verification to a point that it becomes easily added value to the total design process. And this can only be done through automation. The story is out there where, for example, Pat Gelsinger in 1998 said that the cost of testing a transistor became a lot more than the cost of building the transistor. And a company called Mentor Graphics offered a solution that was compression in 2002, where it was able to reduce the cost of testing transistor by an order or two magnitude and bring the cost again below the fabrication of the transistor. And we believe, or I believe, that we're exactly right there. We need to be able to make sure the cost is low enough and the added value is high enough that companies could adopt the technology. What also changed is this notion of Gen AI and the role that Gen AI can play in bringing that low, cost down and increasing efficiency, as well as increased productivity. Just to give you a little bit, that according to Boston Consulting Group, as of today, more than 30% of the semiconductor companies are actually using or integrating AI into their chip design. And more than 50% of them are considering it as well. So majority of the semiconductor companies, and if you go around the exhibition area, you will hear Gen AI pretty much into discussions or offerings by many of the companies. The benefit really is reduced design time, enhanced verification efficiency, as well as low development cost. But what Gen AI does to your efficiency and productivity, using Gen AI to be able to also design a chip based on database that no one guaranteed to be secure, can also induce security. So Gen AI can help you but it can also hurt you. There has to be a way for us to be able to provide a set of solutions to verify security on those designs. So as a result, Caspia Technologies have been developing a holistic GenAI-assisted security verification flow. I showed you that security verification flow, which starts with security linting, then formal, then dynamic. The tools that Caspia is developing that are related to them are called Codex, SVX, and PFX. Codex is our security linting solution. It reads your RTL code, and it tells you where security vulnerabilities or security rules are violated. And this is mainly because we as designers don't appreciate all the security problems that we basically have today. So as a result, it's extremely difficult for designers to write a code that is secure. And this is true for software engineers today as well. It's called blind spot. We have habits in the way we write the code without noticing that those codes could potentially, those code snippets could be insecure. SVX, which is a GenAI-based automated security assertion generator, and PFX basically is a fuzzy penetration platform for dynamic security verification in emulation environment. The three solutions that I highlighted in the previous slide together, they actually provide a very comprehensive security verification. Codex, as of today, checks for more than 150 security rules that ensures that your design is clean against all of these rules. SVX is a GenAI security-focused assertion generator that takes the output of SVX, goes into your formal tool to be able to make sure that during functional simulation, some of those security concerns are removed. PFX is where the rubber meets the road, where you have the entire system into an emulation environment where you're able to verify security considering both hardware, software, as well as your firmware. When you put them all together, this is just an estimate that each of these solutions can cover 1/3, 1/3, and 1/3 of the total vulnerabilities that we know of as of today. And majority of the vulnerabilities that we go after are the common weakness enumeration or CWE type vulnerabilities, in addition to a large database of vulnerabilities that we have been releasing over the past 15 years in a website or a web portal called TrustHub. So Caspia has a grand vision with regard to GenAI. It's called GenAI Security Platform. It basically has a number of agents that work together depending on the task that we try to accomplish. Then it calls appropriate agents, and they perform the task that provides you with the security objective. When you run Codex, it calls various agents. When you run SVX, it calls a number of agents. And in an orchestrated manner, the agents work together to accomplish the objectives that you have. And similarly for PFX. In this case, a designer can actually, through queries, text, or conversation, be able to actually communicate with the system and ask appropriate tasks. Bringing a design, check for linting, show me the assets, what are the threat models, show me a test plan, how can I, show me the policies, how can I check properties, show me the assertions, show me the final reports, and so on and so forth. So with that, I will give a bit of an overview of what we do in Caspia Technology in collaboration with University of Florida in developing the most comprehensive application of GenAI to security or SOC security verification. Just let's take a step back and make a motivation as to why we need this. We need intelligence into developing solutions for security verification. And the intelligence that we bring in requires a number of databases. That requires asset database, rules database, property database, vulnerability database, design or RTL code database, and so on and so forth. And intelligence is needed for identifying the assets, security assets. I'll explain that more. Intelligence is required to understanding those rules that have to be checked. Intelligence is required to developing and understanding security properties. Intelligence also is needed in the way we apply fuzzing. After all, fuzzing is nothing but a random application of test patterns, and we know that that's not going to be effective. And similarly for penetration tests and so on and so forth. We convert all of this into a set of agents that they're able to perform a specific set of tasks. So Caspia's GenAI security platform has 6 layers. Layer 1 is application layer, where user basically interact with the platform and is able to send queries and see the responses. And that could be, again, through text or conversation. The second layer is a supervisor layer, where it receives the information from the user and it starts to make sense of it. It starts to understand what the intent is. I may ask the same question with the intent than somebody else with a different set of letters in English, but the same intent. And the job of the supervisor is actually use LLM to start make sense of that, what the designer intent is. And the LLM is able to actually communicate with the user to make sure that a clarification is given and intent is well understood. And once that happens, it takes that information and converts it into a set of tasks. Once the tasks are identified, it maps the task to the appropriate agents, and then goes to the orchestration layer. In the orchestration layer, it starts to do the task execution. It does agent coordination, and it takes the results, and sometimes it performs self-refinement or self-reflection. Next, it basically gives that task to the agents and then call various agents. We have a total of 6 agents, but each of these agents come in with 2 or 3 sub-agents. So we're looking at total of 12 to 15 total agents that are involved in this SOC, in this security platform. And the agents, I'll be discussing about this more. Then when the tasks are being executed, they require also access to database. And that could be prompt database, embedding, security database, code base, and so on and so forth. And to run these agents, obviously, we have to go to the last layer, which is the infrastructure layer. This is where basically we have a set of GPUs, and many of you know in University of Florida, we have one of the best GPU infrastructure. And Caspia also has its own GPU infrastructure that we use to run our algorithms. Let's take a look at the various agents that we have in the security platform. The first agent is the security verification chatbot. It allows you to be able to communicate, and I'll explain each of these agents in details. The second agent is called security asset identification agent, with the one that you see on the top right. The next one is the security threat modeling and test generation agent. The other 3 include security property generation agent, security vulnerability detection agent, and simulation-based security vulnerability or bug validation agent. So let me elaborate what these agents are. Agent number 1 is your chatbot. There is a help option available in any of the tools that we have today. And the information basically is available for you to read. But when you use chatbot, you can actually ask a question and get an answer. You can use ChatGPT to help you with this. You can ask questions. Can a raw hammer attack directly corrupt FPGA logic? What are the challenges of using formal verification in detecting hardware trojans? How does logic locking help prevent malicious change? Can side channel attack to be prevented using logic obfuscation? These are just some questions that we asked ChatGPT to help us out. And what we got hallucination. We got generic responses that have nothing to do with the question. Basically, there is a lack of knowledge because the answers were given based on the information that they had about software. And the last one is inconsistency, which means that we ask the same question, very similar, but the responses are completely different. With the security verification agent that we have, it has domain knowledge. It understands user intent. It communicates with user to understand what the user wanted to really get out of that question. It pulls information from a hardware security knowledge database as well as real-time information from a quick web search in case the model actually did not have the information that is needed. Incorporates a memory module when a question is answered and is understood. That information actually can go back and be used with the LLM that is responsible for intent resolution, and combines retrieval with LLM generation. We have a database of more than 30,000 unique articles and books and anything you can find for the domain of security verification on 225 security-related topics. And the flow basically takes that information, and what you get is a much more accurate and reasonable information. Let me show you first the question that we posed to ChatGPT. We ask, list all frameworks that use fuzzy techniques for verification of hardware design. It basically gave 9 answers. Let me analyze it for you. 5 of them doesn't even exist. Those solutions are just factually wrong, but ChatGPT just made up the answers. One of them is partially correct, but description actually is incorrect. And a couple of them basically are software fuzzing, have nothing to do with hardware. We posed the same question to Caspia's chatbot. List all frameworks that use fuzzing technique for verification of hardware design. And what we got 8 solutions. We as a security engineer, we looked at all 8 solutions, and all 8 solutions not only do exist, the description of those techniques are also correct, and there is no hallucination. So that's agent number 1. This is available to security engineers to understand problems that they have and get real-time, accurate answer. Agent number 2. If you're performing security, the first question that you ask is that, what do I need to protect? And that's called security assets. Security asset in a design is something that is called worth protecting. Usually we think about security asset in form of encryption keys, biometrics, OCM keys, OEM keys, configuration bits, protected area of the memory, and so on and so forth. And we have many of those. But depending on the threat model, asset could be much bigger than that. When you think about fault injection attack, asset doesn't have to be a key. Asset could be a signal, because by attacking that particular signal or a gate, you would be able to flip a bit from 0 or 1 or 1 to 0 and get access to something very important in the design. For a designer to be able to actually understand and appreciate all of this, not only because we have too many assets, but we also have too many attack vectors, is a tedious task. Sometimes engineers have to spend weeks and weeks and weeks reading specification files to be able to actually understand what potential security assets could be. The security asset identification agent, here we have 2 sub-agents. The first one is called modular spec summarization. And what it does is, it takes your design specification, it takes your design hierarchy, and analyze this information using a bunch of prompting and further analysis. It actually is able to give you a summary of each of the IPs that you have in your design and their security-related information. Then it continues with in-context learning, where we define what confidentiality means, what integrity actually means, and what availability means. And it's able to analyze and generate the first set of asset information. Then we go through some kind of a self-reflection using another LLM and be able to evaluate the response and create a final list of the assets. I'll give you an example that we've been able to run. So in this slide, we have implemented our security asset identification agent on a RISC-V processor. It actually produced close to 100 different set of assets. These 100 set of assets were generated in less than 20 minutes. And it gives you some examples. For example, out of those 100, one is in module 1, the scalar cryptography coprocessor, another one in pulse width modulation controller, and the third one in a UART function. And you can see the information about assets that comes out of the solution. It tells you what the asset name is. It tells you the functionality of that asset. It tells you what the security objective is, which means that if that asset gets either accessed or manipulated, it causes either a confidentiality violation or integrity violation. And it also tells you the justification behind making that decision. So it's a very nicely developed set of objectives to understand what to target when it comes to the sensitive information in your design. The next one is threat modeling and test plan generation agents. This one has actually 3 different set of agents involved working together to be able to provide that information to you. These 3 agents are threat identification agents, test plan generation agents, as well as security policy generation agents. This particular agent has 2 sets of inputs. One focuses on the type of vulnerabilities that are standalone. These are mostly physical type vulnerabilities. And another type of vulnerability that is mostly in the domain of information leakage that could be caused by privilege escalation, TOCTAO, memory corruption, and many other types of vulnerabilities that we have. The upper row actually shows you the physical and supply chain type attacks. It actually gets the security knowledge database. It performs a threat identification agent. It uses a threat identification agent, and it actually it does it interactively with the user. It asks user question. Are you worried about this particular chip to be used in a security critical application? Yes or no? Is this going to be basically subject to fault injection type attack? Yes or no? And it basically continues with asking a lot of questions, and depending on your answer, it adjusts additional questions to get a better understanding of what you think about applications and the type of vulnerabilities that must be considered. It developed a preliminary set of security threats, and based on that threat, it actually provides you with a clear set of test plan. For the second scenario, it actually takes your design specification, it gets the instruction set architecture information, and it performs a security policy, uses security policy generator agent, and is able to give you a list of security policies that you must be concerned about. Use the security policy and is able to give you, again, a set of test plan. Just to give you, again, another example, we implemented this again on RISC-V. It generated more than 100 security policies in less than 30 minutes. And it identified a number of security policies. One is called security policy that focus on attempting to execute a load or load reserved instruction which assesses a physical address within the PMP region without read permission, raises a load access fault exception. It tells you the security relevance. It tells you the potential security threat is unauthorized access, memory access. It tells you the potential verification method, that how you can detect it. It generates, it tells you that you should be using a formal verification method, a simulation, emulation to be able to detect this kind of vulnerability. An impact on security policy violation, it tells you whether it's a confidentiality violation or integrity violation. And you could do the same, and you can see also into other type of security assets that were reported. Then it generates security test plan for each. For example, for the threat category called unauthorized access and privilege escalation, it tells you what the test objective should be. Ensure that the L bit in the PMP entry effectively locks the configuration and associated address registers. Then it also tells you what the test methodology should be. Says use formal verification. You can also do simulation, and it describes how. You could do gate level testing. Then it tells you what the expected result you should be having. It also tells you the evaluation criteria. And lastly, it tells you what tools to use. It tells you exactly that if you're, for example, in your Q&A that you said, I'm using, for example, Cadence or Siemens or Synopsys platform, it tells you which tools from these different companies you should be using to be able to run your test plan. Once you're done with this, then the next step is security vulnerability detection agent. This also has two agents in it. The first one is a hardware vulnerability database creator agent. What it does is that we actually start with a set of known vulnerabilities that we have today. This is actually an open source buggy hardware data set. And with that, we choose one IP, one vulnerability, and we perform what we call replication. This is important for us to be able to increase the size of the data set. Okay? So to do that, we're able to take the vulnerability, the same vulnerability, into different designs with different syntaxes and create variations of the same vulnerability, but increase the total number of designs that experience this vulnerability. And with that, we also send information about the bug itself, as well as design specification. Now we have an expanded hardware buggy database. We feed that information to the LLM, and we train LLM using LoRa technique, and we are able to generate a fine-tuned LLM for bug detection. We ran this on about somewhere around 4,000 vulnerable designs, and as of today, we had close to 85% accuracy in detecting these vulnerabilities. Just to give you an example, this is a fine-tuned LLM detection, bug detection capability that was applied to a vulnerable design, and the design is actually a code snippet that you see for the password verification logic within RISC-V. And in this case, basically the password authentication requires the input hash to be equal to the correct hash. And if it's not correct, it's supposed to be asking you a couple of more times, and at some point, basically, it's going to block you. But the way that this particular design is implemented, it never blocks you, which means that it gives you unlimited try to be able to figure out what the input key should be. And that's obviously is a security violation. The next one is a security test generation agent. This agent also has 3 sub-agents in it. The first one is called test case generator agent, test bench generator agent, and bug validator agent. The way this agent works, it takes your RTL code with the bug explanation, and it creates test cases, which is basically an explanation of various conditions that have to be developed inside your design so you can actually create a test bench for those conditions. And that is done with the first agent. That information is given to the second agent, which is able to actually give you an actual test bench to run. Then that information is given to the next one, which basically takes the test bench information, as well as your RTL code and your bug, and try to validate that this bug actually does exist. And that is important. Once that is done, not only you basically prove that the bug exists and you have a way to test it, you take that particular design as a known design, as a buggy design, add it to your database. Now the size of your database keeps increasing, and this allows you to be able to develop a much more fine-tuned LLM for your vulnerability detection. This is another example, given the RTL. It's a password authentication module, and on the right side, I'm not going to read the code for you, it's the generated test bench. You can take this test bench to provide proof that that vulnerability actually does exist in the design. Another one is a security property generation agent. Okay? And this agent is able to combine a structural RTL analysis and user-supplied threat vectors to filter relevant CWEs. We have a database of all the CWEs. We have a database of all the threat models. We've already done a manual work to be able to map various CWEs and threat models, which basically this is available on the CWE web page itself. Then by doing that, you get the input You have the assets. By mapping them together, you actually, and your user input, you know exactly what threat vectors you should be considering. You take that information, and then you do the mapping with the CWEs, and then that becomes the threat model vectors that you're looking for. Take that information, give it to our security property and assertion generation agent. It gives you a list of properties. We use another LLM to do self-reflection, and then at the end, we get the final system Verilog assertion list for that particular vulnerability. This is another, again, example of the password authentication module. And on the right side of the slide, you see the list of the assertions that are generated to be able to test for the particular vulnerabilities that we are considering. So you could see how in Caspia Technologies, we're able to take advantage of GenAI to be able to provide a lot more comprehensive set of security solutions in a more automatic approach to you. So the takeaway is GenAI is real, is here to stay, is going to improve efficiency, is going to actually provide a lot more comprehensive set of results and capabilities. And for those who are in the company, you don't need to have security experts to be able to run security solutions. You rely on GenAI approaches to do that. However, it comes with some challenges as well. One of them is a lack of hardware domain-specific knowledge. In Caspia, we believe we have access to the largest database of security knowledge that ever existed. But that doesn't mean we have everything. We don't know exactly what attackers are doing and working on. There should be some 0 days, etc. But GenAI gives you this ability. Imagine this. If today we hear a news that a new vulnerability showed up somewhere on the web, all we need to do is to give that information to our GenAI platform, takes that information, understand the vulnerability, convert them into a set of policies and rules, it verifies the check, and it tells you whether that vulnerability is covered or not. If it is covered, that's great. If it doesn't, it provides you the solution. That's the vision that Caspia Technology has. So as a result, you don't have to invest in people trying to constantly catch the next particular vulnerability that may be out there that you may not be aware of, because Caspia is going to be doing that for you. Necessity for the fidelity of the response, very important. Many of you could ask me a question after this presentation. How confident are you about the result? Right? And this is why in every solution we do a lot of self-refinement and self-reflection to be able to try to the best of what we can. And a lot of, obviously, with the human in the loop, our engineers are able to verify a lot of results that we have, but we need more of it. Inconsistency in response. Well, LLMs are known for this. So bringing domain-specific knowledge, it actually reduces the inconsistency quite a bit. And same about the hallucination, which I really believe that once you bring a comprehensive domain knowledge to LLM, it actually becomes more deterministic and it becomes much more accurate. With that, I'm going to end my presentation, but happy to answer any questions you may have.
Mark, quick question. First of all, good job in putting all this together and articulating this excellent surgery for Microsoft. The question is, do you have a super agent that supervises all of this? You alluded to lack of readily available engineering expertise here. So is there a way to just, for an engineer who doesn't know anything about security, to trigger the process and then be beneficiary at the end? And I have one sub-question. You referred to fine-tuning, and my question is, are you actually fine-tuning a commercial model by changing weights, or is there something else that you meant by that?
So the first question about a super agent. So yes, we have as part of the GenAI security platform, we actually have an orchestration layer that is responsible, which is an agent itself, that is responsible in understanding user intent, identifies the tasks, and then perform task assignment and decides whether the tasks are run in series, in parallel, which input has to go to be output of the which input is coming from output of which agent, and so on and so forth, given the objective of that question that came from the user. So the orchestration layer with supervisor layer together. So you came in a little bit late, so I talked about it in one of the slides, that the user basically communicate with the supervisor layer communicates with the orchestration layer then communicates with all the agents. The second question is fine-tuning, and the answer is yes. We actually fine-tune the weights using LoRa approach, which I mentioned. So it really goes in and provide changes into the weights and biases. We use RAG technology, RAG framework quite a bit, actually, in our work as well, except for the vulnerability detection is actually a fine-tune based approach. Yeah.
So my question comes from the point of view of good and not evil.
Yeah.
Is you go to the middle of your presentation, you talk about vulnerability detection. Can I turn it on its ear and generate an attack?
Yes.
With your tools, and thus, red team my design?
So the answer is yes. Can I be more clear about that? So attackers can take advantage of GenAI and be able to use similar analysis and be able to identify vulnerabilities, that areas that they can actually potentially cause vulnerabilities as well. And that was actually my slide number 2 or 3, which I talked about the good and the bad of GenAI, right? But what's important is that you're going to have a series of solutions available to you, not only to take advantage of what GenAI can offer you, but to also be able to verify what GenAI can do to your design.
Well, the nature of my question is a little different in that, and I think it was sort of in the middle of your presentation when you talked about your vulnerability detection agent.
Yeah.
And so the methodology I think of is you use that to generate an attack on, say, a derivative design, and thus discover if you have a vulnerability in that new design. So you're using it on yourself.
Yes.
And is that sort of a workflow, or is it really redundant? The vulnerability is already detecting stuff.
Right. So not through the agents that we develop, because at the end of the day, agents are going to be implementing the task we defined. But can an agent be able to assist an attacker to be able to identify a particular vulnerability and use that as a way to be able to inject it into the design? And the answer is again, yes. Right?
Thank you.
Question for you about what are you seeing as far as the effects of security violations in verification?
Effects in terms of?
So what are the problems? What are the attacks that are happening within verification today?
Yeah, so the verification today is a functional verification, right? The way I describe it is those who do functional verification may get lucky to actually detect some security verification, but they don't know it. I'll give an example, okay? So for example, we ran a spyglass on some of the designs, and we ran our solution, which is Security Linton, on a design, okay? Spyglass reports to you a lot of violations. We as a security engineer have to go in and analyze every one of those violations to see if any one of them is security violation. And that is a very tedious task. But if you use Codex, anything that is reported by Codex, 100% is a security violation. So what we do, we basically bring a unique solution that is able to tell you what's wrong with your design with regard to confidentiality and integrity violation, that other solutions at this point, they don't have that capability.
How many companies are actually looking for security violations within the verification flow?
I would say everyone. So not allowed to disclose anything, but 7 out of the 10 semiconductor companies has our solution right now as we speak. Many of the automotive semiconductor companies, data center semiconductor companies, as well as military primes, that they are very much interested in using our security verification solutions.
It doesn't seem like we've been talking about this as much as we should.
I think it's been around for long, so it's time for companies to take security seriously. Any other questions? Yes.
Thank you for your presentation. The question is, how your agents learns how to detect hardware trojans? And another question is, since LLM has a limited number of input tokens, how it checks very large SOC designs?
Yeah.
So
question number one, how does the solution detect hardware Trojan? Hardware Trojan is nothing but a circuitry injected intentionally or unintentionally that cause confidentiality violation or integrity violation. And all we do is detecting those confidentiality and integrity violations. So yes, our solution are able to assist with detecting anything that causes those sort of violation. Question number two, token. It's a huge problem. We use a lot of time divide and conquer to be able to deal with it. You cannot simply have a large, very large design to be able to run through some of these LLMs, especially that we use, we perform all our analysis at this point on open source LLMs. So there's always a challenge with token. Good question. Okay, well, thank you very much, everybody. I appreciate it. Enjoy the rest of the day.